In this video, we're going to learn how to use integration to find volume of a region generated by rotating a curve either around the y-axis or the x-axis using the disk and washer method. So the basic idea behind what we're going to do is we're trying to find the volume of a solid. So if I have a loaf of bread, that is a solid piece. If I wanted to find its total volume, well, I could take each slice and I could find the area of each slice. And then to get the volume, I could add up all of those areas. And the thinner my slices are, the more accurate my my volume will be. So we're going to use that same concept to figure out the volume when I rotate a function. So here I have x equals f of y, and I rotated it around the y-axis. So my rotation went this way. And essentially what I'm going to do is I'm going to look at a disk. I'm going to slice one piece of this, right? The very top is a circle, the middle is a circle, the very bottom. I keep getting all of these circles, and the radius keeps changing, but I can find the area of all of these circles and then sum those all up, add them all up. So I could take the limit of all of these areas as my radius goes from 0 up to its max, and then work through that. Well, we know when we're taking a limit to find an area or a volume, when we're taking that sum, it's just our integration. So each of these slices in this picture is just a circle. So to find the area of my circle, I have my radius times squared times pi, right? Area of a circle is pi r squared. So to put it in terms of our picture, this radius is going out to whatever the x value is all the way out. So instead of calling it r, I'm going to call it x. So now I have pi times x squared. Now notice my radius is perpendicular to the y-axis. So I'm doing this with respect to y, right? My thickness is respect to y. I'm stacking these in the y direction, so I have to do it in terms of y. If instead I had turned this whole thing, I would do it with respect to x. So we have to pay attention. So wherever my slices are made, whatever they're perpendicular to, tells me which variable I'm integrating with respect to. So here's just our integral of the area of those circles, and then we'd find our bounds. So let's actually try one. It says find the volume created by rotating y equals x squared on the interval from 0 to 3 around the y-axis. So here is my graph. It's a nice parabola, and as I rotate it, I'm going to get these slices. Okay. Now each of these slices, right, are perpendicular to the y-axis, so I need this in terms of y. So I can't call this function y equals x squared. Instead, I need to say that it's the square root of y equals x. Now, I could say that it's the plus or minus y, but we're really only going to be focusing on this piece over here because that's my radius. Okay, so to find my volume is the integral, and my lowest y value is 0. My highest y value, when I plug in my 3, remember we're only going from 0 to 3 on the x-axis, 3 squared, this point up here is actually at 9. So I'm integrating from 0 to 9, pi times my radius, going out here, which is square root of y squared, dy. So my volume is the integral from 0 to 9 of pi y dy. Pi is my constant, so this is pi times 1/2 y squared from 0 to 9. So I ran out of room over here, so my volume is going to be pi over 2 times y squared is 81. When y is 0, it's going to be minus 0. So my volume is 81 pi over 2. So here we want to find the volume when y equals 4 minus x, so there's my graph right here, is rotated about the x-axis on the interval 0 to 4. So if I'm going to rotate this, the graph's going to come over here. And I'm still going to get a disk, right? I'm not worried about an inner piece just yet. So here's my disk, and I need that area. So my volume equals the integral, and I'm going along the x's, so from 0 to 4, of pi times my radius, which is from here to here, which is going up to the curve the square root of 4 minus x, squared dx. And again, just finding my integral, so I have the integral from 0 to 4 of pi times 4 minus x dx. So this is the integral from 0 to 4 of 4 pi minus pi x dx. So this is 4 pi x minus pi over 2x squared, evaluated from 0 to 4. So I'm going to have 16 pi minus 8 pi. 4 squared is 16, 16 divided by 2 is 8, minus 0. So this volume is 8 pi. Now if we were rotating around the x-axis, and I only have one function f of x, I would have a washer here, a whole disk here. But now what we can do is we can have two functions, and we get a washer. So there's an inner radius and an outer radius. And in order to get that area of just that slice, we would have to do pi times the outer radius minus the inner radius. So it's the same setup. Because my slices are being taken perpendicular to the x-axis, I would do it in terms of x. So again, rewriting that formula out, the volume when I take a washer, meaning I have two functions and I'm just looking in between, I have the integral of pi times the change from the outer radius minus the inner radius, the big radius minus the little radius, dx, because this one in my example is with respect to x. If I had done it vertically around the y-axis, I would have to have pi times f of y squared minus g of y squared dy. So here we're going to see one that requires us to use a washer. So we have the region bounded by y equals x squared, which is our blue, this graph, and we have y equals the square root of x in red, which is this graph, and we're rotating around the y-axis. So when I do that and I rotate over and I make my slice, I can see that it's just this region. So I have this outer radius to get to the inner radius. That's the radius of what this shape is going to be. So remember, I need these in terms of y, not in terms of x, because I have to differentiate with respect to the y. So here I'm going to say the square root of y is equal to x, and over here I'm going to say y squared equals x. So to find my volume, it's the integral. Now I'm going on the y, so the lowest point is 0, and x squared and y squared are going to equal right here. We want to know where they meet. They're meeting when x equals 1. And so it's pi times the outer radius, the blue, which is square root of y, squared, minus the inner radius, y squared, squared, dy. So I can clean that up a little bit. So I have my volume equals pi times the integral from 0 to 1 of y minus y to the 4th dy. So this is pi times 1/2 y squared minus 1/5 y to the 5th, evaluated from 0 to 1. So this is pi times 1/2, 1 squared is 1, minus 1/5, minus zeros. So I have to do my 1/2 minus 1/5. So I have pi times 1/2 is equal to 5/10. 1/5 is equal to 2/10. So I find that this area is 3 pi over 10. Now for this one, we're given the region bounded by the line y equals 4 minus 2x, the x-axis, and the y-axis. So we're looking at this triangular region, and we want to know where will we get the greatest volume, if I rotate around the x-axis or the y-axis. So we're going to do both. So let's start with going around the x-axis. So just to sketch my picture, I'm going to continue out my graph. It's going to come over here, and I know when I make my slices, here's my radius, everything has to be in terms of x. So I already know that my boundary here is y equals 4 minus 2x, that's my radius. And I'm going from when x is 0 to when x is 2. So to find my volume, from 0 to 2 of pi times my radius, 4 minus 2x, squared dx. Okay, I can pull out my pi, so this is pi, the integral from 0 to 2 of 4 minus 2x squared dx. Now here you can multiply out the 4 minus 2x and integrate. You can also use a u substitution. I'm going to go with a u substitution. So I'm going to say u equals 4 minus 2x, which means du equals negative 2 dx. Now I'm missing the negative 2, so I'm going to multiply by negative 2 over negative 2. That's equal to 1, so nothing's changing. But now I have pi times negative 1/2, because this guy moved outside. The integral, changing my bounds, 4 minus 2 times 0 is 4. 4 minus 2 times 2 is 0, of u squared du. So I have negative pi over 2, and I'm integrating u squared, so that's going to be 1/3 u to the third, evaluated from 4 to 0. So I have negative pi over 2 times 0 minus 64 over 3. So now it's positive 64 pi over 6, and I'm going to simplify that. I'll get 32 pi over 3. So that's my volume when I rotate around the x-axis. So now we want to compare that volume to rotating around the y-axis. So if I'm rotating around the y-axis, these are still going to be washers. Here's my radius, but now I need this solved for y. So if I add the 2x to both sides and then I subtract my y, I'll have x equals 2 minus 1/2 y for my radius. So to find my volume, it's the integral, and I'm going from the y, so it's from 0 to 4, of pi times 2 minus 1/2 y squared dy. And now again, to integrate, I can multiply this out. I prefer to use a u substitution, so again I'm going to say u equals 2 minus 1/2 y. So then du will equal negative 1/2 dy. Now I'm missing the negative 1/2, so I need to multiply by a negative 1/2. And to undo multiplying by a negative 1/2, I have to multiply by a negative 2. So now I'm going to rewrite this as my volume equals negative 2. I'm going to bring out my pi. The integral, and I'm changing my bounds, 2 minus 1/2 times 0 is 2. 2 minus 1/2 times 4, 1/2 of 4 is 2, 2 minus 2 is 0, of u squared du. So now I have negative 2 pi times 1/3 u to the third, evaluated from 0 to 2. So I have negative 2 pi times 1/3 u to the third is 0, minus 2 to the third is 8, so minus 8/3. So I have negative 2 pi times negative 8/3, and I get positive 16 pi over 3. So in this case, we had a larger region when we rotated around the x-axis. We had 32 pi over 3. This time we only had 16 pi over 3. So it depends on which way we rotate what type of volume we'll get.